Okay, so I'm not going to edit this out because I think it's just too funny. I had to compose myself there. Turns out that the answer is there's 26 freedom and constraint space types within the FACT library. But I've been lecturing on this all day, so that's why my brain is mush here. So, but you get to see this raw lecture in its rawest form here. So, okay, so we'll pick up right where we left off. So let's say we wanted to find the constraint space of this freedom space. Okay. Could you find, and this is very common, say you wanted to have a flexure that just rotates, okay? It's a single rotation axis. That's one of the most common flexures that people want, is just give me a flexure that rotates, okay? It's a cross, or it's a like a revolute joint in rigid mechanism land, right? Well, say you didn't know the FACT chart and you just wanted to find its constraint space so you could know everything in there, or so you could visualize all the designs. Can you think of a shape that would represent every possible blue line that could intersect that red line? There's obviously a lot, right? Because there's just 1 degree of freedom. So 6 minus 1 is 5. There's 5 non-redundant independent wrenches, pure force wrenches in there, and they linearly going to make a huge subset of infinity. But can you think of some geometric shapes? Well, in my master's thesis, I thought of it as like, okay, this sphere, every single blue line in the sphere that intersects that point would be in there, and every sphere marches all the way along there. So you can imagine every single sphere at every single point along the red line would work, and so that would capture most of the lines. But then there's all the blue lines in the box that are parallel to the red line. So I believe if you look at my master's thesis, you'll see I draw this constraint space like that. But it wasn't until my PhD thesis I realized, well, there's a much more elegant way you can represent all those lines. Those are all the blue lines, by the way, conceptually. That's the conceptual correct way to visualize all the blue lines. But a more elegant way to package it is just a bunch of intersecting fully blue highlighted planes, right? So every single line on any of these blue highlighted planes, if you take every plane that intersects that red line and make it filled in with all blue lines, then that will contain all the lines from the last example. So this is how I started representing it and how it's in the final FACT chart. Okay, so it's like a cool realization to realize that every single design lies within there. So there's a number of papers out there where people publish a paper on, hey, I found a new rotational joint. And it's like this is a very famous one. This is a cross pivot flexure where the blades here are they lie on these intersecting planes, which is why it only achieves a rotation. Now, by the way, cross pivot flexures are amazing. They maintain their stiffness over a huge range. They have very high load capacity and do an amazing job. So it's a brilliant flexure, and this deserves its own paper, to be honest. But there's a lot of papers where people keep designing things that look totally different. This is, by the way, how you could assemble it. But like, for instance, this looks totally different. This thing also achieves a rotation. It's grounded in these two back ends. The reason it only gets that rotation is because these intersecting planes, their blades, lie on these intersecting planes. Oh, gosh, I really need to take a break here. But anyway, that's why it it achieves that rotation. Okay, and it looks completely different. Here's how you could make it. With this, you put some bolts in there to clamp it with these things in there. Okay, that would be one way to do it. And then here's another totally different looking example where it's got 4 blades connecting these two bodies that also line these intersecting planes. They get a rotation as well. Now you might say, well, this one gets a screw because as it rotates, it actually pulls in. But remember, FACT in these degrees of freedom, FACT is only laying out the degrees of freedom, which implies no motion ever occurs. It's just the first instantaneous motion that's permitted. It's the direction of compliance. So before this ever deforms, it actually is a pure rotation. Then as it rotates to other infinitesimal increments, it actually screws in. But still, and whereas the other ones don't. Although this one, the axis of rotation actually drifts as it moves with a certain parasitic error. But anyway, FACT doesn't consider that. FACT doesn't care about that. That's a higher level analysis. It finds before it even deforms what the instantaneous initial, axis of or direction of highest compliance is, or axis of rotation. Okay, and so they all have the same initial instantaneous rotation, and the reason is because all their flexures lie on these planes. And so what I was saying is a lot of designers will just keep publishing papers, and it seems like they're very creative and they have these really neat new designs that look very different than these three, and they keep coming with these rotational flexure joints. But once you know the secret that all designs lie in these intersecting planes, all these new designs stop looking very novel and creative, because it's like, well, they just all lie on those planes. So if you have this knowledge, you have this huge advantage, because you can already visualize every design. It's like every design anyone throws you is like trivial, because you know they lie in these intersecting blue planes, and as long as you have 5 independent constraints in there that are independent, right, then it'll achieve this rotation. Okay. All right, so that's kind of the power effect. So I'm going to show you now from start to finish how the fact design approach works, and really all you need to know. Okay, so here's a simple version of fact here. Okay, so say I had this example where I've got this stage, and it's got this little probe tip up here, and I want to constrain it to some ground with a parallel flexure system, so that it achieves a 3 orthogonal intersecting degrees of freedom, rotational degrees of freedom. Okay, so which is basically a spherical joint, right? If you got a ball in a cup, for rigid mechanisms, you get 3 intersecting rotations. So let's make a compliant version of a spherical joint. Okay. Okay, so how do you do this? Okay, so the first step of the fact design approach is specify what degrees of freedom you want. Okay, and that's honestly the hardest step, to be honest, is knowing what degrees of freedom you want for any given application. A lot of designers don't even know. What you need to ask them is when a customer comes to you and you're designing a flexure, is say, well, what degrees of freedom do you need to be compliant? And then what directions need to be constrained, and then what directions you don't care if they're constrained or if they have degrees of freedom. That's really how you want to package it, right? Because sometimes they know they want certain degrees of freedom, but then they don't care about others. They're like, if this is a degree of freedom, it's no problem, but if it's constrained, it's no problem. But these directions absolutely need to be constrained. And when they sort out degrees of freedom in those 3 categories of degrees of constraint, degrees of freedom, and things that don't matter, that's kind of how you want to think about it, and help them realize what things absolutely need to be a degree of freedom, what things absolutely need to be constrained. And then the other things, it can give you more sets of possible degree of freedoms that you can pursue different designs to get what they want. Okay, but in this case, say they know for sure they want these 3 to be compliant, they want everything else to be absolutely constrained. Okay, well, what you do is you can go right to the fact chart. So there's 3 things there. So you go right to the fact chart and you can look in the 3DOF column, because they gave you 3 degrees of freedom. You look in the 3 degree of freedom column. You've got 9 options here. These are called types. 9 types. Okay? So which type, you're not familiar with all of them. You're familiar with this top one. You're not familiar with these. You've seen some of these, or you're at least familiar with these shapes. You're going to get familiar with these, but you've got 9 options. So what you do is you pick, and there's always one correct one, right? The degrees of freedom they list will always go to one correct one. And in this case, you can see the correct one, by the way, will contain the degrees of freedom they want, okay, with as few extra ones as possible. Okay, so like, for instance, those 3 intersecting rotations may be in this one, right? This one has 5 degrees of freedom, and it's just a bunch of intersecting red planes. You could pick 3 intersecting rotations in there, but it's got way too many other things going on. There's 5 independent things where they just gave you 3, right? So don't bother looking in higher, any of these other columns. Look in the 3DOF column, and it's got to contain it. There's no other shape in here that contains all 3 intersecting rotations except this one. Okay, and you should already know Okay, so you know, you can see hopefully the 3 orthogonal intersecting rotations are in that one. But you could already know that, right, these 2 will make a disk. Those 2, if you add together, will make a disk. And those 2 will make a disk. So you start adding all these things from disks, and you start generating a sphere. Okay, so that's the sphere of rotations. And then here's your constraint space that it links to. What, you know, again, you don't even need to find it. You just trust the chart. So really all you've needed to do is specify what degrees of freedom you want, look in the column, where the appropriate column, and find out which space in that column contains those degrees of freedom. Okay? There it is, and then here's your design space. Okay? So the first thing you tell your customer is, they said, I want those 3 degrees of freedom, I want everything else to be constrained. Well, you can say, well, if you want those 3 degrees of freedom, you have to get all these as well. Okay, they may not realize they also have to get the combinations. Okay, so say, you know, are you okay getting every rotation that intersects that point? And if they say no, then say sorry, because you live in reality here, and you can't just get those 3 and not get their combinations. So say, you know, here's what you have to get, but that's the fewest permissible motions that contain the ones you want, with as few extra ones, and everything else will be constrained. So they say, okay, fine. If you tell me that's how reality works, then that's how reality works. Okay. So then you say, well, your design space is this. That's it. Okay. If you want a parallel system where you connect this stage directly to a ground, your design is going to come from there. And you know, okay, then how many? And say they want it to be exactly constrained. Well, how many wires do they need to pick then? Well, if you go back here, you know, you always just take that column number, say 6 minus the number of degrees of freedom, and it will tell you how many non-redundant things there are in there. So 6 minus 3 is 3. So you know you have to pick 3, okay? And so that's the design space. You don't have to pick 3. Now what you could do is pick sub-constraint spaces, okay? So what you could do is look in my master's thesis, and you'd find there's just one sub-constraint space. And you'd be disappointed what it says, because hopefully by now you would know what the sub-constraint space would say, okay? Because this is a very simple one, okay? So anyway, my point is you could either look up in my master's thesis the sub-constraint spaces, or you can deduce them yourself. And I guarantee with a few more hours of practice of this, you'll be able to deduce them all yourself, okay? The sub-constraint space for this one says, it's just one sub-constraint space, right? It says, pick your 3 lines from this sphere so they don't all lie in the same plane. That's it. So it's, you know, there's not like that. The one sub-constraint space we did from the past had 5 different, or sorry, from that one constraint space we did in the past, it had 5 different sub-constraint spaces. This one just has 1, and it just says pick your 3 lines from the sphere that don't all lie in the same plane. What would happen if they all lied in the same plane? Well, then they'd be a disk, and a disk only contains 2. Okay? So as long as you don't pick your 3 so it makes a disk, you're good. Okay? Okay. So a couple other rules of thumb. Once you know how many to pick, once you've picked your sub-constraint space, in this case we only had one option, and once you know how to pick them, it's generally wise to select your constraints as far away from each other as is possible, right? So constraints are kind of like electrons, right? They like to be as far away from each other as possible. They like repel each other. It's better. And the reason is because if you separate them, they'll resist moments better, and they'll just be more solid designs, and they'll exhibit their freedom spaces more clearly. You know, or it's like people on a bus, or right. So it's like when you get on a bus, everyone, you know, sits as far away from each other as possible, so it's not socially awkward. And then only when the whole bus is full, the seats are full, people start sitting next to each other, right? So it's like people on a bus or you know, electrons, they repel as far away as each other as possible. So the furthest you could pick 3 things from this sphere apart would be 90 degrees in kind of a tripod. Okay. Now, if you're limited to do 90 degrees, any other angle would be fine, you know. But it would be nice to make it symmetric, to have them the same angle apart, and make it nice and symmetric. And you know, this is where the common sense of the designer comes into play here. And so what you do is you pick these 3 all with the same angle apart. Again, the most stable is 90 degrees, but if you can't deal with that, it takes up too much space, do less, it's fine, right? And then just make sure you pick your wires so that they connect the 2 stages, right? Connect that stage to that stage. and connect that stage to that stage, and you see where the wires are drawn. Okay, and then you have to use your common sense to know how to fabricate them. And so you can see we made these with different Z-shaped kind of or weird-shaped kind of parts that could be bolted onto the face of this ground and this stage. And remember, we added this lip here, so it moved the strain down and everything. So anyway, the cool thing is FACT at every step. First of all, it doesn't have many steps, and it's very simple, and it shows you all possible designs. Okay, but it allows input from the designer the whole way for every step of the process. Okay, and sure enough, if you do it, you get your degrees of freedom. And here's the mode shape. So again, the steps of FACT are: pick the degrees of freedom you want. Be very careful in your selection. Look at the FACT chart. Look in the column that corresponds with it. Find the freedom space that contains those. Look at its constraint space. Determine how many things you can pick in that constraint space to be exactly constrained. Then look up or deduce its sub-constraint spaces and pick those so they're non-redundant. And then if you wanted to over-constrain this for whatever reason, say for whatever reason you weren't smart and you didn't want to have things be axisymmetric. By the way, axisymmetric is always awesome. If you can spread things 60 degrees, it's always magic in nature, right? But say you wanted 4 wires, you were stuck to some square-looking tripod. Well, then you could pick a 4th one, spread them all the same distance apart, and it would be over-constrained. It would be redundantly constrained. Or maybe you wanted to redundantly constrain it just to stiffen it or increase its load capacity without changing its degrees of freedom. So maybe it wouldn't be such a bad idea. But anyway, you can see how this works. And the approach is great because, because you can visualize every possible design, you can consider all the possible designs with all the different sub-constraint spaces. And again, my master's thesis has the sub-constraint spaces for every single of the 26 constraint spaces in the chart. You can comb the entire design space and have very high confidence that you've considered all the possibilities and therefore have the best one. Remember, topology optimization just falls to a local minima. This one can almost guarantee you're going to find, the global minima, because you can consider them all very rapidly and conceptually. And you can infuse your common sense at every step of the process, knowing how it needs to be fabricated, knowing these precision principles, knowing you need to lower the strain at the joint, knowing how you're going to assemble it, and knowing things should be symmetric as possible, and knowing whether it should be exactly constrained. So you can make beautiful looking things that really look like true machines that aren't all organic and strange, and make them follow all the principles of precision to design these things. So that's really some of the power and advantages of the FACT approach. Okay, so let's do one more example, and then that should wrap all this up. Okay, so say you wanted to design an array of micromirrors. Okay, turns out if you have micromirror arrays, you can do all sorts of crazy things with light, right? So say you had, you wanted to design, a big imagine a checkerboard of thousands of little, square mirrors packed side by side, just like a checkerboard. Okay, and say you wanted these mirrors to tip and tilt. Okay, independently. You can have actuators below them, or wherever you need to tip and tilt these guys independently. Well, then if they're small enough, a millimeter or smaller each, and you can very quickly control them and rock them back and forth very, very rapidly, then you can basically make a mirror that can take any light that bounces off of it and redirect it and do whatever you want to it in any way. And there's all sorts of neat applications I can tell you at the end of the lecture for that. Okay, but say someone came to you and said, I want to design this micromirror array that gets tip and tilt. Okay. And it's got all these constraints. My range has to be plus minus 10 degrees. The speed has to be 4 kilohertz. The settling time has to be 0.2 milliseconds. Again, a lot of this stuff, FACT is not going to do. FACT is going to get the degrees of freedom, and then you get to tune its geometry and its material properties to get this kind of stuff and pick its actuators and stuff. But a real person would come to you and give you these specifications, and they'd say, Well, obviously the mirrors need to be as close to each other as possible. You don't want much dead space between the mirrors because that's like, the light will fall between the inside and you won't be able to reflect or control as much light. You'll lose light, first of all, so it won't be as efficient, but also it might heat stuff up behind the mirror and burn up your electronics or something. So you want as little light to spill between the cracks as possible. You want the actuators, you want the actuators and constraints to be either right on the side of it or below it, preferably below it, because if on the side of it, it spreads them out. You want them to be as close to each other as possible. You obviously don't want it to be above them because it'll block the light, okay? And you don't want the mirrors to collide during operation, obviously, and you want to be able to fabricate them on a sub-millimeter scale. So these are all the things these are the constraints, things you'd consider with your common sense that would be very difficult to teach a computer that has an automated approach. By the way, FACT can be automated, and I am automating it. And I'm developing a SolidWorks add-in that can step you through it, but could also automate and just generate a bunch of designs. But you'll always get the best designs if you step through with it. But anyway, and the reason is, as you step through with it, these things, these constraints, just wherever you have them in your brain, and you can consider them as you design it. And then these specifications, like I said, you can tune once you get a good topology that gets these degrees of freedom you want. Okay, so what you do is you'd say, okay, let's pretend the person that came to me and said they want this micromirror array to do tip tilt. Let's say they know what they're talking about, and that's what they actually want. Okay, they want everything else to be constrained. So great. So let's look at FACT. We wanted those 2 degrees of freedom. It's in the 2DOF column. So again, you've got 9 options, which is the most options you'll ever have. When you get into 1DOF or 0DOF, 4DOF, 5DOF, you have much less options. Okay, and so you'd have to find which type, that contains those 2 within the 2DOF column. And if you go through these, I know you're not familiar with many of these. Probably the only 2 you're familiar with is this and this, right? And these ones are kind of weird and filled with screws and stuff. But anyway, you will become familiar with them by the end of this course. But anyway, you should know anyway that if there's 2 intersecting red lines, they get a disk of red lines. Okay? And even if you didn't know that, you could look through and very quickly find that 2DOF type 1, okay, is the freedom space that contains the 2 intersecting rotations. So the constraint space is this, okay? That there's 2 DOFs in here, so how many non-redundant constraints do you pick in here to be exactly constrained? And by the way, you might ask yourself at this point, do you want this to be exactly constrained? Well, it would be really nice because we're controlling light reflecting off mirrors, so you care about precision. So if you are going to over-constrain it, it better be something that isn't assembled and is like as little over-constrained as possible. Because in this case, you do care about precision. Okay, you definitely want to use the full deformation of these flexures to steer the light. Flexures is it's by far the best bearing option to steer light for this application, right? So, okay, but they lie. The wire flexures are going to lie within here, or the constraints will lie within here, and you know that there's going to be 4 you need to pick because 6 minus 2 is 4. Okay. Okay. And by the way, you just learned from the last example how many things are contained within a sphere. Okay, I mean, going back to here, there's 3 things in a sphere, right? So they contain the 3 degrees of freedom, and the constraints contain the 3 non-redundant constraints. Okay, so spheres always contain 3. That's another thing to memorize. Discs contain 2. Okay, spheres contain 3. Planes with parallel lines contain 2. Filled-in planes contain 3. Boxes contain 3. And I think that's what you have memorized so far. Okay. Okay. So great. So fantastic. So there's 3 in this. You have to pick 4 in total, and there's 3 in this plane, and there's 3 in the sphere. That saturated those. That's how much they contain, independently. But together, they contain 4. Because 6 minus 2 is 4. Okay. Okay. So you go back to the guy that hired you and says, "I want these 2 things." It's like, well, you've got to also have everything in this disk. Which they would want, right? They'd be stupid to just want tip and tilt. They should want rotations about everything in the disk to steer the light in any direction, right? So they'd be thrilled with that. Okay, and then you can say, okay, well, here's your constraint space, and you got to pick 4 things. Okay. Now, what you could do is you could either look up in my master's thesis the sub-constraint spaces for this constraint space, and there's only 4. Okay, there's rarely more than 5 for these. That's the good news. This one has 4, and you could probably deduce them right now. Okay, so I'll show you what they are. Because already, if you've internalized what I've lectured on, you could start already coming up with your own sub-constraint spaces. Okay. So the first sub-constraint space says pick 3 from the sphere that don't all lie in the same plane, because it would be a disk, and then 1 from the plane that doesn't intersect this point here of the sphere, or it would be part of the sphere. Okay? Okay, because remember, a sphere only contains 3, and a plane only contains 3. Okay? It saturates after 3 for both of them. Okay? So that you should be able to deduce this now. Okay? And I haven't written the words here, but that's, if you look at my master's thesis, that's what it says. Okay? 3 from the sphere that don't lie in the same plane, and 1 from the plane that doesn't intersect the sphere. Okay? Okay, then the other thing you can do is you can pick 2 that intersect from the plane, and 2 that intersect from the sphere, that of course would form a plane. Okay? Basically a disk and a plane, and you got to make sure this angle isn't 0, 180 degrees, because then it would be on the plane. It would like be picking all 4 from the plane, which it can only hold 3. And then you want these 2, if they're going to intersect, to the intersection point from this axis, or from this intersection point of these 2 planes, to be non-zero. Because if they're 0, well, first of all, if these 2 points coincide, then it's 4 from the sphere, and that's no good. But even if they don't coincide, if this is 0, it's on there, it's those interlocking disks, which you already know is a different freedom space. Okay, so it's those things that are the little tricks, okay? But anyway, if you follow this, if these aren't, if this is, pick 2 from the sphere and 2 from the plane that intersect, this is not 0, and these things aren't 0, 180 degrees, you're good. Okay? Then the other thing you could do is pick 2 from the plane that are parallel and have angles here that aren't 0 or 180 degrees. And in this case, it would be a different freedom space. That's another thing you probably don't know yet, but you will. Okay, but trust me, these angles can't be 0, 180 degrees. And then this of course can't be 0, 180 degrees. Okay, and that would work. And now the final thing is pick 3 from the plane that don't all intersect at the same point. That includes a disk and parallel lines at infinity. Okay, that intersect at infinity. And then 1 from the sphere that doesn't lie on the plane. Okay? Those are the 4 ways you can pick sub-constraint. Those are the 4 sub-constraint spaces, and therefore the 4 ways you can pick your 4, in this case, non-redundant constraints, so that they're non-redundant, so that they're independent. Now remember, the number of constraints you're picking has nothing to do with the number of sub-constraint spaces. The last space we did an example for had 5 sub-constraint spaces, but there were only 4 non-redundant constraints. This one had 4 non-redundant constraints, but just happened to have 4 sub-constraint spaces. Okay, so what we're going to do is so we have 4 options here because we have 4 sub-constraint spaces. So we're going to design, we're going to visualize and consider every possible way you can make a parallel system mirror that's exactly constrained. Okay. Okay. So all right. So let's look at the first sub-constraint space. Remember, we want 3 things from the sphere that don't all lie in the same plane, and 1 from the plane. Well, now you use your common sense to say, okay, maybe this would be the best way to make that single mirror. But remember, they've got to be arrayed and stuck together all in a thing. So here's the mirror. Say, okay, well, obviously, if we want tip tilt on the surface of the mirror, right, we're going to need a wire on the side and tuck it close to the side so we have space. And then we need 3, and of course spread them out as much as possible in a tripod, but make sure you could make it. So it's like, okay, that would be an exactly constrained mirror, and you could pack it in an array, but I don't like it. First of all, good luck making this in the microfab, or in the clean room. Okay, angled tripods, wires, that's kind of crazy. And there's not a whole lot of symmetry. You've got this random thing. It would get tip and tilt, but because there's not symmetry, they would drift. The axes of rotation would drift over large range, and they wouldn't, they'd just be kind of a mess. So I don't like this design. This is probably not a promising sub-constraint space. Okay, so fine. So try another sub-constraint space. Try the second one. Pick 2 from the sphere and 2 from the plane that satisfy these conditions, and there you go. Okay, this way you have just 2 angled ones below, and now two things on the side. Again, you could array this potentially, but it would also be